Okay, let's restart. And now we are learning about the dynamics of open chain robot. So the dynamics is the actually most difficult part of our class. So actually in the previous my intelligent robotics class, which is the undergraduate student class, in the class we also deal with the dynamics. In the case of the undergraduate class, we used the Newton-Euler method and the Lagrangian method. Similarly, we will start from the Newton-Euler and Lagrangian method. But in case of modern robotics class, we will deal with the dynamics using and twist and the concept of wrench. So I will introduce about this one. So sorry. Actually, in the kinematics, there is there is configuration space. So X, Y, Z, these kind of things are configuration space variable, and the joint space variable is theta 1, theta 2, etc. This kind of things is joint space variable. So transformation between these things is done by homogeneous transformation. Homogeneous transformation, and the between the x dot and theta dot, we have there is a relationship using Jacobian. So until now we learned about this kind of things. So this one is position level, this one is velocity level. So we call this one is kinematics, and we call this velocity kinematics. So if the theta joint space variable is given, and then if we find x, this one is forward kinematics. And if the x, the configuration space variable is given, and if we find the theta joint space variable, then this one was inverse kinematics. So this one, these are things about the kinematics things, and from now on we will learn about the dynamics. The dynamics thing is about the force and acceleration. So we are in dynamics, we deal with these relationship. So acceleration means x to dot or theta to dot, and these kind of things is related to the force or torque. Force torque. So this relationship is about dynamics. So generally the inverse dynamics equation is having this kind of form. So tau, this one is torque. Torque equal mass matrix multiplying theta dot, theta 2 dot, and then this C value, C is about centrifugal acceleration, centripetal acceleration, and Coriolis. And this G term is about gravity. So usually we call this inverse dynamics equation as equation of motion. Sometimes we call this EOM. And generally, if we saying robot dynamics, that indicate this inverse dynamics equation. So in this equation, if we know the acceleration information and position and velocity, we can calculate the torque, the joint torque tau. So using inverse dynamics equation, we can find this torque value. So this one is about dynamics. So we will deal with about this one. When we're doing this, we will use the concept of positive definite matrix. Actually, this M is mass matrix, and this one is symmetric positive definite matrix. Symmetric means the matrix having same with same. So this part and this part is same, and positive definite means if there is M matrix and if we multiply n by 1 some arbitrary G matrix, G vector here and here, G transpose and G, and then because the dimension of this one is 1 by n, n by n, n by 1, so it becomes some 1 by 1 scalar value. So if this scalar value is positive, we call this M matrix as positive definite matrix. So if you want to know more about positive definite matrix, you can check this link. I will share about this one. So for the reference, just remember the M matrix is positive symmetric positive definite matrix. So in the dynamics, there is two kind of things. Actually, in the kinematics, there was two kind of things: forward kinematics and inverse kinematics. Similarly, in the dynamics, there is also forward dynamics and inverse dynamics. As I already told, the inverse dynamics is when the theta dot, theta 2 dot is given, we find the torque. So this equation can be used when we robot control. So if you are going to control the robot, you should command some position, or sometimes we should command torque. So just think as this arm is robot arm, and if you holding this kind of water bottle, you should exert, you should hold you should make some torque in the arm. So if we know the angle of this one, and if there is some desired velocity and desired acceleration, for doing that, we can calculate the torque, then make that kind of position and velocity and acceleration. So sometimes we call this one as computed torque method. Computed torque method. So for the computed torque method, we can use inverse dynamics. In case of forward dynamics, if we reverse these two terms to here, and if we take the inverse of M matrix, in the case we can make this kind of equation. So in this case, if we know torque, then torque and theta dot, that means position and velocity and torque, then we can calculate the acceleration. So in the forward dynamics, we calculate the acceleration. So if we know the acceleration, we can integrate acceleration 2 times, then we can find the theta. This means we can define the position or velocity of some rigid body object. So this kind of forward dynamics can be generally used on the physics engine. So in the computer simulation, we have several physics engines. The famous one is ODE or Bullet, or there are many kind of simulation engine. So by using this, we can make some simulation, computer simulation. So for that purpose, we can use forward dynamics. So in this class, we are focusing on the inverse dynamics. So there is 2 kind of formulation method. One is Newton-Euler formulation method, and the other one is Lagrangian formulation. Actually, Newton-Euler method is more general and recursive. So this method having this kind of property, and Lagrangian formulation is more simple and convenient. So, but there are pros and cons. So sometimes I prefer to use these 2 things together. So if we make some dynamic equation, I recommend you to use these 2 things. So if you need the verification of dynamic equation, you can make the dynamic equation using this one first, and then also you make the same equation using Lagrangian formulation. Then compare these 2 results, and then you can confirm the dynamic equation is correct. So I usually use these 2 methods together. So in our class, let's review Lagrangian formulation first. So in the Lagrangian formulation, there is a concept generalized coordinate. So the generalized coordinate means the independent coordinate to describe the system. The independent coordinate to describe system. So actually the generalized coordinates means the minimum coordinates combination to describe the system. So that is very optimized coordinate to describe system. So if you define the generalized coordinate, there is generalized force. So if the generalized coordinate q is theta 1, theta 2, x, so this one is about the rotation. This one is about the translation. So in generalized coordinate, you can deal with these two type of variable together. So when we use this kind of Q, we can define the generalized force F as tau 1, tau 2, F. Because this one is about rotation, we use this one as this one about rotation. And because this one is translation, also F is about the translation. So the Lagrangian formulation is like this. The L is Lagrangian function, and this one equal is kinetic energy, and this one is potential energy. I think the concept of Lagrangian is not the new one. Actually, if you are majoring mechanical engineering or similar one, you might learn about the Lagrangian formulation already. So I will briefly introduce about this one. So using this Lagrangian function, if we take partial derivative of L and then time derivative again minus partial derivative using Q, then this becomes F. And this F is generalized force. So this becomes this equation becomes the inverse dynamics equation. So let me see the example. There is point mass, and the mass is m. So this one is kinetic energy, and this one is potential energy. So the L Lagrangian function becomes like this. And if we take the partial derivative using x2 dot, x dot, it becomes like this. And if we take the time derivative again, it becomes m zeta 2 dot. And also, if we take the partial derivative using x, it becomes minus mg. So the f d dt partial derivative x becomes like this. So this one becomes inverse dynamics equation, and this becomes forward dynamics equation. So in more complex case, there is 2R planar robot. In case of 2R planar robot, let's see the process of using Lagrangian formulation. Firstly, there is point mass M here and M1 here, M2 here. And there is zeta 1, zeta 2, and there is gravity here. And x1 and y1, the position of x1 and y1 becomes L1 cosine 1, L1 sine 1. And if we take the time derivative, it becomes like this. And x2, y2 becomes like this. And if we take the time derivative, x2 dot, y2 dot becomes like this. And from the Lagrangian function, the k minus p is L, and the force, generalized force, becomes like this. And there is, because this one is about the, this equation is about the single rigid body, but if there is multiple rigid body, we should sum from I equal 1 to 2, I equal 1 to n. So in this case, there is 2 mass. So we sum position, the kinetic energy 1, 2, and minus position potential energy 1, 2. So if we calculate this one, and this one is kinetic energy 1, kinetic energy 2, this one is potential energy 1, potential energy 2. So if we calculate L, and if we calculate this one, then when the I equal 1 and I equal 2, we can calculate this equation, the inverse dynamics equation. So the result is like this. So I hope to see this site. In my intelligent robotics library, there is example 1, R type robot. In here, I used Newton-Euler method, and here the Newton-Euler method. So using this one, I calculated the dynamic equation. So this one is M matrix, this one is C matrix, and this one is G matrix. And using Lagrangian method, I also calculated the equation of motion. So this one having same result. So we can confirm, or we can check the result is correct. So I want you to see this library, and in here I want to explain the meaning of the result. This mass matrix having symmetric positive definite matrix form. So this one is mass matrix, and this mass matrix is function of theta. So it means the moment of inertia is changing depending on the theta value. That means joint position value. So in this configuration, there is moment of inertia, and in this configuration, there is different moment of inertia. So because moment of inertia is depending on the position, so there is the moment of inertia is always changing depending on the theta. And also the C value contains the centripetal torque, and this one is Coriolis. The Coriolis term is the multiplication of different joint velocity, and in the centripetal acceleration there is a square of joint velocity. So the square things is about the centripetal acceleration, and different the multiplication of different velocity becomes Coriolis term. So actually there is different acceleration. One is centripetal and the other one is centrifugal. So this one is related as action and reaction. So so if there is a car, and this car is turning this way, in this case this car should exert this kind of acceleration to go this way. So this one is centrifugal. In this case, the person inside of this car exert this kind of acceleration. So if you turn the handle like this, then the person feel the outside force. This one is centripetal. So this one centripetal in Korean we call this one is 원심력, and the centrifugal in Korean 구심력. So these two things is different. So it is important to careful to call this kind of acceleration. And the last G term is about the gravitational torque. So the general formulation about the N-link open chain robot, there is kinetic energy like this, and potential energy. Potential energy like this. So if you take the partial derivative and time derivative and minus like this, then we can calculate the inverse dynamics equation. So this one is the result of N-link open chain robot. So this one is mass matrix. It becomes like this term, and this one becomes G term, and this one becomes C term. Actually, the C term also can be obtained from this calculation. This one is Christoffel symbol. This one is Christoffel symbol. It seems a little bit complex, but that's not that difficult. So there is IJK. So if you take this kind of partial derivative calculation and 1/2, then you can calculate C theta dot. This one is centripetal and Coriolis term. So this kind of things are also done in the intelligent robotics library. So in this equation, in this library, we calculated C term using mass matrix and Christoffel symbol. So this one is the result. So these two things is same. So we also confirm the system is properly solved. So that's it. Actually, this one is stretching about the dynamics. Actually, preparation of dynamics of open chain, dynamics open chain. So we leave you the Lagrangian formulation, and the next class I will explain about the real dynamics, actual dynamics of single rigid body using the modern robotics technique. Okay, let's break a little bit.